Okay, the last session, it's a little bit shorter, which I'm sure both of us are happy about that. So I just want to clarify a few things. First, the Bitcoin stuff, it wasn't that the standard Bitcoin hardware as is could be used for garbled circuits, which a few of you talked about. The idea would be that the resources and planning that were used to develop those chips could be captured and reused in order to build hardware for garbled circuits. I wanted to make that clarification. The second clarification is Ben Riva came up to me afterwards. We had a little discussion about the claim I had that you only needed one-way functions, and I have to. He brought up a very good point. So I think I might be overlooking something, and we'll resolve it by tomorrow or Thursday as to whether an extra assumptions is needed or not. And the other great thing that even Demgard told me was that they have this extremely fast commitment scheme that for all of these protocols might be plugged in to several aspects of those consistency checks in order to speed things up. So what was the big lesson of all of that? Which is that every aspect of this problem that I have studied, that I've thought had come to some sort of like endpoint as to what else could happen. The turnip is dry. It's like squeezing blood from a rock. Not true. Every aspect, every time, I've been wrong. So it means that I'm always cutting short the vision of what could possibly be achieved. So it's very optimistic, and it means great. It means like that there's still possibly a long way to go. And part of that is this what I want to talk about now, which is garbling. I'm going to review some of the stuff we talked about, so there's a little bit of overlap from what Yuda discussed this morning. But at the end, I want to discuss this vision I have or this idea that might be able to also break through bottlenecks for garbling circuits, and that's joint work I have with Valerio and Tal Malkin. Okay, so we saw that originally this classic garbling has these 4 rows, double encryption with some sort of range detection and so forth. I'll go through this rather quickly. And of course, you permute those things to make sure you don't leak the truth table, etc. And then this Beaver-Macaulay-Rogaway permute bit, so you can always add extra bits to these wires so that the evaluator can know directly where exactly the work has to be done in order to decode properly. And as we discussed, in order for all of those security proofs to work, we need this simulation property for garbling, which is essentially one needs to be able to simulate a garbled circuit using only the description of the function and the output. And that's the only sort of real property that you need: the correctness, which is the obvious property up there, and the simulation property. Okay, so I guess as an overview for this type of section, let's briefly review all of these different techniques for garbling, and then let's ask our questions as to whether what else can happen. When I first realized, when I first heard about these free XOR and this garbled row reduction and so techniques, and I think many people in the community assumed this is kind of like a bottleneck, you can't really get past this, and recently Zahur, Evans, and Rosalick have gotten past it, and then they've opened the door to, I think, other further extensions. And that's really critical, because as we've seen from all those performance numbers, much of the time, 99% of the time, for large circuits is spent in garbling. And all of the communication is also in garbling. So all the expensive things of secure computation happen with this garbling. And this hardware vision I have for this thing, it will also be driven by the communication as opposed to the computation, which can be done in silicon and so forth. So this is a critical idea, this free XOR garbling, that essentially one can take the input wire for each of this gate, make this A0, make this B0, make the 1 value just the A0 value plus some random constant, make the 1 value for B also just B0 plus some random constant, and have that same property for the output. So the output wire is just the XOR of the input wires in both cases. Right? So that's a great idea from Kolesnikov and Schneider. And the evaluator can just simply XOR this thing. If you have the right assumptions on your cryptographic primitive, this will work. So these are great techniques, but the question I want to pose here is that all of this work has worked under the has used this idea that gate by gate garbling is the best strategy for coming up with the randomized encodings of functions, and now we're going to try to investigate whether this is how we can get beyond this idea. Again, first we'll try a few things which don't work. So, well, first, let me first discuss why I think gate by gate might not be so good. So this circuit right here comes from some sort of this circuit comes from an AES, from part of the AES S box. And so here's the plain model circuit, and when we translate this to a garbled circuit, notice that each of these AND gates here are going to require a cryptographic hash function applied. So as I mentioned before, one of the key aspects of performance for any of these protocols is parallelizability. And circuit depth is the natural theoretical measure of parallelizability. If you have a very low depth circuit, you can run all of the components in parallel. On a GPU, you can run them all in parallel. When you do gate by gate garbling, it means that the circuit complexity of the original circuit that you're evaluating, it's going to be multiplied by the circuit complexity of your hash function, of your cryptographic primitive. Every AND gate in the original function is going to have to take a hit in terms of parallelizability by the circuit complexity of your cryptographic primitive. Does that make sense? So if I only needed to compute 2 AND gates here in order to run this circuit, now I have to compute a hash function here, wait for that to finish, and then compute the hash function here. And so that adds a delay that limits the parallelizability. And so gate by gate, this is going to be implicit. So I wonder if there's a way around it, and that's what's driving the rest of this. Okay? So in sentence, if the depth was d, then now you're going to do depth d times the depth of your hash function. Okay. The second question, I guess, is does gate by gate, is actually that the most communication efficient? Can you garble smaller if you garble in a different way than gate by gate? Okay, so those are the two questions. Is the depth complexity of garbling and the size complexity of garbling? And those are overheads of secure computation. As I mentioned in the first slide today, this is a good direction. If you look at where the overheads are, see if those are necessary or not. Okay, so alternatives. There is one alternative that I know, this AIK paper, Applebaum, Yishai, Kushilevitz. They do garbling for arithmetic circuits. Wonderful idea, great abstraction, and their scheme for that requires the LWE assumption to do garbling of these arithmetic circuits. And I think that's a good direction to try to see if that can be removed and so forth. And I haven't drawn the full connection between that work and this work. So let's consider alternatives to gate by gate. And in fact, Yuda talked about one this morning right here. It says instead of thinking gate by gate, what we can do is take an n input gate. So if you have a function that has n inputs, then just like he talked about this morning, then like with 3 inputs here, you can come up with a truth table of 8 values using this standard triple encryption and so forth. And that's going to take 2 to the n rows. Okay? And that's good, but in fact, I don't think that that's going to ever work out in practice. So there is this Boyer-Peralta lower bound. So what they did, they asked the question, let's say you have a function on 2 n variables, any Boolean function from 2 n variables to a bit. They ask, what is the AND complexity? And they have this notation C AND. What is the number of AND gates you need in order to compute that function? And what they showed was this recursive construction. They say, take this function right here, and what you can do is sort of factor. You're going to do two sort of things. For the first n variables, what you're going to do is factor the first variable x1 out. And then you'll have, so this function f can be represented as x1 times some other function of n minus 1 variables, plus some other function of n minus 1 variables, right? You just factor out the x. And so now you have two functions on n minus 1 variables, and you do the same thing. For each of those functions, factored into x2 times two functions of n minus 2 variables, and so forth. So you run that recursion n over, so basically n levels, and then for the bottom of the recursion, you just compute every single function of those two n variables. And if you do the analysis on that construction, you basically get that the circuit size in terms of AND gates for this will always be will be at most 2 to the n plus 1 minus n minus 2. So what does that say? If I have an n input, a 2n input gate, if I garble it this way, it'll take 2n rows. If I garble it using this, deconstruction right here, it'll take at most 2 to the n plus 1, which is like roughly, if you change the notation, here it's 2n, right? This would be 2 to the 2n, right? So it's roughly square root number of gates, AND gates, if you decompose it into ANDs instead of using an all-in-one garbling, okay? So so what that says is, in general, for maybe specific cases it's good, but for in general, as we consider larger and larger circuits, this type of thing is going to be beaten by this not trivial, but this basic upper bound on circuit sizes. So we can't do Mongo gates in general. That's not going to help us. Yeah. So that's basically the computation. This would be the size of garbling them just using AND gates, and it'll be less than the big gate. All right. So we need a different idea, and again, I'll bring up my analogy here as we consider more and more advanced. Eventually, we'll get to Mr. Transformer here. So as discussed earlier this morning, there's this garbled row reduction technique, which is a very good way for getting rid of one row. So what's the idea? That what we can do, C0 here, when we garble a gate, C0 is an unconstrained variable. So instead of just picking it randomly and encoding all of this, we can just implicitly call this value 0, okay? And then backward solve, decrypt and decrypt, in order to figure out what C0 should have been, right? And so what we can do is, randomly, so pick one of these rows to set to 0, randomly, and then solve in reverse for what C0 should have been, and then continue from that. And that's a good way for getting rid of one row. From any truth table you want, here's a good technique for getting rid of one row. Everybody feel happy with this? We've seen it twice now? Okay, good. So 3 rows, not 4. Good. And thankfully, this technique is very nice, because this technique only left C0. It only defined C0. It allowed us to pick C1, and so with free XOR, we can just pick C1 to be C0 plus R. So good. This is 3-row reduction plus free XOR, and this is good state-of-the-art for many implementations, from the past. Okay. So of course, with n minus 1, we can shave off a row for this type of thing, and so on and so forth. But it's still better to use these AND gates, because when you shave it off here, you also shave it off when we talk about the complexity of that thing. Okay, good. So step 2. So this was we were in the situation where you get 3 rows plus free XOR, or in that same paper that did the row reduction, there was a cool idea for 2-row garbling, and I want to give a sort of sketch for how that worked. Okay, so we want to garble this gate with only 2 rows, and we're going to view this problem as secret sharing. And this is also secret sharing. The reason I introduced this, secret sharing is going to be an insight for how for a further extension. So what's the idea? What we're going to do, what we need in terms of secret sharing is the following. Some value. So if the evaluator is given A1 and B1, they're going to be able to compute this hash of A1, B1. So no matter what their input wires are, they're going to be able to compute this hash of these input wires. And for an AND gate, what we need is a secret sharing scheme with the following property. So given this information in this gate right here, G1 and G2, if I was given this value, I need to use these three secret shares in order to reconstruct C0. If I was given these three values, I need to reconstruct C0. If I was given these three values, I need to reconstruct 0. But if I was given those values, I need to reconstruct... okay, but I think the labels might be... okay. There's a typo on the slide, but we all get. The point is, in this third case, we need to recover C1. Okay? So how can we implement this? We're going to use the way that we know how to do secret sharing, which is Shamir, yes. So what we're going to do is take hash of, we're going to take, see the yellow point, the points I use yellow for, yellow, 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 okay, and blue. So yellow is 1 comma this point, yellow is 2 comma that point, and 3 comma that point. We are going to interpolate a degree 2 polynomial using these 3 points. This is not a degree 2 polynomial because, because I'm taking poetic license for what an interpolation is. So this is a curve, a general curve, okay. But the point is we can define green points here at 5 and 6. So these 3 points, 5 and 6, are all on this curve right here. Great? And in fact, the 0 of this is C0. Okay? Now, given that I described to you how the scheme works in the previous slide, how do I create C1? Which one? Yes, I'm going to interpolate what you said, which is that you interpolate between green, green, blue, okay, because that's 3 points. Now we interpolate a degree 2 polynomial between these 3 points, and that's defined C0 and C1. Okay? So that is how this secret sharing works. Now, what is the downside to this secret sharing approach? For those who quickly saw my next slide. Yes?
You need to send these points?
Well, okay, actually, so good point. Let me step back. To garble now, the gate information right here, the gate is just going to be G1 and G2. So all I need to do is send, this is G1 and this is G2. So my gate only needs to have these 2 green points. This is good. Previously I needed 3 values, right, 3 ciphertexts in my gate. Now I only need 2. I just need these 2 green points, which are points in some finite field that's big enough and so forth. Then in order for the evaluator to interpolate, evaluator gets one of these points, either yellow, either that yellow, or that blue. And the evaluator basically takes these 2 green points plus whatever point they get, they interpolate a polynomial, and they get either that point or that point. And that's how the evaluation works. So that clarifies. There is still one problem with this scheme. What have we sacrificed in our... What? Yes, why have we sacrificed free XOR? Because we have no control over C1 and C0, right? These things no longer differ by R. So, as I said before, life is sacrifice, and here we have made a sacrifice with this case. So, the question is this a sacrifice that's necessary or not? Okay? And then, so, of course, our general question of is gate by gate the best? You see still here, it's probably better to use normal AND gates here because XORs are not free in this, and so general circuits, you sort of lose out. Okay, so that's one of these characters here. Payman Mohassel, another person who's also made excellent contributions to this area, and Mike Rosalek had this flexor garbling idea, and I want to present this because I think it's a very, very, very good idea. What they noticed is maybe we can get the best of both worlds, okay? Because what they started doing was they started coloring gates. They said, notice that in this path right here, so this AND gate right here, if we use the 2 the polynomial sharing garbling, we know that the difference between C0 and C1 is going to be some fixed constant, right? We can't control it. It's not the R that we like, but it is some R. So maybe what we do is we say, this gate right here, we're going to create a free XOR gate using whatever constant was induced by this AND gate. Just said, in the red gates, all the gates that color red will have a particular offset R red, okay? And therefore, all of the XOR gates that are colored red will be free. Okay, so then they decided, well, what I can do is also color this gate right. If I color these inputs right here red, then this gate will be a 2-row XOR. These two gates will be 2, and this gate could also be 2, because it comes from here. And then one goes on coloring. So one says gates. So gates of a particular color will only require. So for example, these red gates will require, red AND gates will require 2, this blue gate will require 2, this purple gate will require 2, etc. And then whenever we change from one color to another color, we just give a special 1-row gate which changes that color, which is just a translation, so to say, between one offset to another offset. Okay? So using this gate coloring idea, they were able to show that all of these gates require either 0, 1, or 2. So all of the XORs require either 0 gates when they're free, 1 gate when you only need to translate 1 wire, and 2 gates when you need to translate 2 wires. So it's kind of a good way to merge these two techniques. Okay, okay. So this is what I think. So from that was 2013, and this is 2014. So again, when you think the turnip is essentially totally dry, comes an idea from I don't know where it comes from, but it's an inspired one. So what they realize is the following. You can take they call it half-gate garbling, but I think as I said, the punchline is that I think it could be generalized beyond this. So they say, take a look at this AND gate. What I'm going to do is highly counterintuitive. What I'm going to do is inside this AND gate, I'm going to put 2 more AND gates and an XOR gate. Okay? But the constraint is that this AND gate will be this will be an AND gate in which one of the parties, so this value z will be some random bit. Okay? So it'll be in one of the gates, I'll maintain the constraint that the evaluator knows the input of one of the wires. And in the other gate, I'll set the constraint that here the generator knows z. The generator, when it's garbling, picks z. So this is an AND gate in which the generator knows one of the input bits. This is an AND gate in which the evaluator knows one of the AND bits. This one right over here. Okay? And if we are able to garble these two gates right here, then the actual output, A and B, can basically be represented by this. A and Z plus A and B and Z. If you just extend this, this thing will cancel out with that distribution. Okay? So this is a nice thing. We expand it out to some larger thing. These gates are AND gates, but they're special kind of AND gates. And then if we satisfy that these two support free XOR, then this XOR gate will be for free. Okay? Very good. So in fact, yeah, those are what they know. So let's handle the case of garbling where the generator knows this bit Z. Okay, so the generator knows this bit Z, and there are input wires. In particular, the generator picks this bit Z randomly. Okay, and this wire is normal, so it has an A0 wire and an A1 wire. Those are the labels for that wire. And so what we're going to do is we're going to say that C0 here, C0 and C1 are the output labels, and if Z is equal to 0, then we know that the output wire will always be C0, right? So the garbling that we're going to give is just if the person has A0, then we'll give this particular wire, and if the gate is A1, we'll give that wire. And we'll use the selection bit for the guy to pick which of these two rows to do. So he'll know exactly which one to pick. He'll pick the right one, compute the hash of his input, and XOR with that entry in the gate, and compute the right wire. So the Z0 case, done. The Z1 case is essentially, now if the input wire was A0, the output will be C0. So again, we'll have the evaluator just hash this and take an XOR. And if it was 1, then the output wire would be 1. Okay? So what I've described, the generator is going to pick Z, know which case it's in, and decide to garble this gate either with these two rows or these two rows. Okay? So basically what I've constructed is this special gate. It also takes 2 rows. Okay. I've garbled this gate and it takes 2 rows. Based on the techniques I've described before, what can we do to make this a more efficient garbling? Garbled row reduction. We know that whenever you have a gate, you can apply this technique. When you have an unconstrained variable, set one of them to be 0. Okay? So in this case, we'll just set C0. We'll set that row to be 0. Randomly, we pick one of them. Let's call that row to be 0. In this specific case, what that means is if this row is 0, then C0 has to be that, right? Okay, good. So once you have C0, that means the garbling for this gate only takes 1 row. And similarly, if we set that to 0, the garbling here only takes 1 row. So it's either that row or that row. Okay? So now I'm able to garble this gate with exactly 1 row using garbled row reduction. Okay? And of course, setting up free XOR just means setting this wire to be the R value, right? So we're using garbled row reduction and free XOR just like we did in the previous case. Very good. And that's, once we do that, either the garbled row here is either this value or this value, depending on whether 0 or Z is 1. Okay? And if you look at it, all you do is you always take this hash right here, and you just add R whether Z is equal to 0 or 1. Okay? So it's very simple garbling here. You just hash and hash in parallel, and then XOR with R at the end.
What is your game?
What is the game? Well,
You have instead of having one gate, right? You have 2 small AND gates and so, right? You still need to have 2 capacitors.
So-
You have some.
so yes, you're going. So I only talked about this particular case, but you guessed the punchline. So here, I first garbled this with 2 rows in a standard way. Then I applied all the tricks I knew, GRR and free XOR, and this gate now takes 1 row. I will then show how this gate also takes 1 row, and now this entire AND gate takes 2 rows, but it's compatible with free XOR. Okay, so that's this right here. Once you know this trick, once you know this construction I just described, right? Describe the circuit as like blah, blah, plus blah, and then apply GRR and free XOR. You can reconstruct this all the time. That's why I present it this way. So I'm using the same exact trick right here. If we had time, then I would have you guys reconstruct it yourself. If you fully understand the technique, an exercise would be to say, okay, the evaluator knows this bit right here, B plus C, doesn't know A. If B plus Z is 0, then this is what the garbling should be. If B plus Z is 1, then this is what the garbling should be. And now apply the same thing. I want a garbled row reduction, and I want to do the free XOR. Question?
But the evaluator is not garbled.
Yes. So the point is, the garbler is going to garble, okay? And the garbler is going to garble, and in this case, notice that, what does I want to say? So the point I want to make is that the garbler is still garbling. The garbler is going to garble this particular row and then share B plus Z. It's going to leak B plus, this bit right here, B plus Z, is going to be leaked to the evaluator. So at the time of evaluation, the person will know that bit and will sort of know which construction, which construction to be in. It'll be exactly the same in the previous case. The the bits that are needed will be the same. Okay, so the analogy, I guess, the cute analogy I wanted to make was with the moment when physicists realized there'd be particles that are smaller than the subatomic particles, and they found one, and then they found many, and then they found many, and then of course came the standard model of theory where you have like 50 of these like bosons and muons and blah 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 blah. It was like an insightful moment in physics when we realized that the world was composed in particles that are smaller than that. So this is what I think that this analogy for this construction is that the world is composed in smaller than just gate by gate construction. There's something to be said about that. Okay, so from this realization that that one could garble in that particular way, the three of us are working on basically garbling polynomials. So the first step is we're looking at one can look algebraically at how this garbling is working. So one can think of it in terms of picking random values a, b, r, and so garbling is going to be a linear function of these 7 things for AND gates. It's going to be some random label A, some random label B, some random label R. For this is for like the left wire 0 value, the right wire 0 value, etc. And then the hashes of just these values. And if you can think about the inputs that the evaluator is going to get, the evaluator is either going to get A or A plus R, depending on what the value of that, whether that input wire is 0 or 1. And similarly, it's going to get either the hash of H of A or the hash of H of A plus R, which corresponds to that row. And similarly, for the B wire, the evaluator is going to get these 2 particular values, both the original label and the hash of that label. And then this value right here represents what the garbling of that gate would be. So in this, if we actually compute this algebra, the input, the evaluator is either going to get this row, like this row, this row, this row, this row, and then the garbling of the gate right here, which is running those 2 constructions in this way. Okay? It's just this matrix times what these strings are. And from these are the 6 strings that the garbler knows, and then the evaluation procedure is just going to be taking a linear combination of the rows that it has. So if we take exactly the construction that Zohar Evans-Rasilek created and ignore their description of it and just say, here's what's happening in terms of their garbling as linear algebras. The garbling is this function right here, and the evaluation is this function right here, taking the rows that you have and then combining them in this particular way. Okay, and if we just do the algebra, you will basically see that here, VB plus VB, right? So VB plus VB, if we do the dot product here, you basically get, it's easier to look at this right here. Since this here is constructed by taking this matrix and this right here, this first bit is going to be multiplied here and here, so that's going to be a 0. This second bit right here is going to be 0 times b, which will be this right here. This term right here, if you do the algebra, you'll sort of see that this is VB times little a right there, plus, so if we take a look at this particular term, I'm going to expand it out on the very next slide. And if you trust the algebra that I've done, essentially the row that one computes is going to be AB times these 2 random bits that were leaked times the random R, the free XOR component, plus a bunch of hashes of the input wires. Okay, so I sort of admit that I'm not explaining this in the clearest way. So one should view this as a linear garbling scheme. One should note that it will correctly support the free XOR based on this linear algebra property. And then one asks, why should this scheme be secure? To argue that this garbling scheme is secure, I suggest that what one has to do is first make some argument about this hash function. Basically, let's call it a random oracle for the sake of this argument, that all of these particular values are going to be completely random, and then we'll make a rank argument about this particular matrix. So there are 6 rows here and 7 values here. We're going to argue through rank argument that R is never in the span of the rows that the evaluator has. And so intuitively, if the garbling scheme I've shown is correct, which means that the evaluator is able to produce an output wire, but if R is not in the span of this particular row, they can't produce the other wire. And so R is hidden, and also the other wire is hidden. And that will suffice for the simulation property that we sort of need. And this is where I'm sort of being quite informal. But I guess what we've discovered and what we haven't been able to explain properly yet is that one can expand this particular construction. So for example, here is a matrix and a set of values that allows one to compute the garbling of this sum of quadratic terms. So AB plus BC plus AC. One can compute this with just 3. So this again is the input wires, input wires, input wires, and these are the 3 rows that are used for garbling. Okay, and so what this shows is that one can compute the sum of quadratic terms using only 3 rows. Okay, and so one can, in particular, one can extend this. So any quadratic polynomial in n variables, we can garble using n ciphertexts. Okay, and so the trivial way for representing this, if I just wanted to garble this right here, this particular predicate, would require 1, 2, 3 AND gates. Okay, and our garbling will, so 3 AND gates using that previous technique as default would take how many rows? 6 rows, and now we can do it using only 3 rows, 3 ciphertexts. Okay, and you can expand this to be, if you have 100 variables, you can compute any quadratic polynomial in 100 variables. So each term is just, it's a polynomial that's a sum of monomials, and the monomial is at most degree 2. That's the thing that we can compute, and it takes 100 rows, no matter how many terms you have in there. Okay, now this is a little bit of cheating because one other point I want to make about this construction is that this construction only makes it makes non-adaptive queries to this to the cryptographic function. So the only calls to the oracle we're making are based on the input wires that the person has, and this is going to be true of all of our constructions. For we're going to do this for degree 3, for degree 4, etc., etc. We're only going to have to make non-adaptive queries to the oracle, to the cryptographic primitive. Now, why is that something that we would want in a construction for garbling? Yes? Yes! Good. So it reminds me of the story that Silvio said. I don't know if anybody has heard it, but with me you can use the same strategy. So Silvio almost failed his hardware quals in grad school, and he didn't take the course. He decided to skip it, and then his advisor Manuel Blum orchestrated some special purpose thing that he could pass his quals in. And Silvio didn't know anything about hardware, so he comes to this exam, and the person starts giving him questions like, why would we use a TLB with the blah blah blah? And he said, of course, performance. And he said it in a way that would make the questioner wonder why I'm asking such a simple question to the person. Of course, performance. And then of course these questions came again. He said, of course, performance. And then of course, performance. And then it came to the multiple choice question where he had the questioner drew a few examples on the board and said these are 3 answers. I'm going to ask you questions. You tell me which solution would apply for that. And Silvio, there are 3 answers, and so Silvio would, of course, the person would ask a question and say, of course, and point like that to one of the in the middle of two rows and do a little adaptive searching here. So of course, when I ask you a question like, why would we want to do something like this for garbling, after having talked to you about parallelizability as the main important thing, you can always answer that for the rest of this. So parallelizability is why we want to make non-adaptive Oracle queries, because then when we have higher depth circuits, the best way to do this with AND gates would be gate by gate by gate, which requires adaptive queries. You garble the first AND gate, then you have to use the result of that to evaluate the next gate, and you have to use the results to evaluate the next gate. That's how you get that multiplicative factor in the depth of your evaluation circuit. Here, with this approach, one hopes to avoid that and just do additive. You just have to compute the hash function once. So we can do this with non-adaptive queries, and we have generalized this. So for example, we can now also compute degree 3 terms, and a degree 3 over 3 variables only requires 6 rows, but if we do degree 3 over, and in general, this is the let me not put theorem here. I will play, this is our claim. We're still writing out the paper for this. But every example we've developed, we can fit into this particular model. So for example, degree 3 polynomials over 4 variables, we can garble using only 10 rows. And if we take this particular construction out, take 100 variables, and consider any variable 3 construction, we can garble any variable 3, degree 3 polynomial over these 100 variables using like 100 times 50. So basically around 5,000 rows, and that's any polynomial over this. So in terms of, we win in terms of both non-adaptivity, because in this case every standard gate by gate garbling of a degree 3 polynomial requires 2 ands, one on top of the other, and so as a result, you're going to have adaptive queries, whereas we can garble this in non-adaptive queries. Additionally, so circuit lower bounds are very hard to come by, but if one takes a random selection, take degree 3 terms over 100 variables, right? There are 100 times 99 times 98 of those, right? So that's like 100,000 of those. Take 50,000 of those. Take a sum of 50,000 of those. So now build a Boolean circuit gate by gate for this. It's going to take, we don't know what the circuit bound for this is, but if you do this in a naive way, it's going to take tens of thousands of AND gates, whereas in our construction, we only need 5,000 gates. So as we go for low degree polynomials, garbling, this approach seems to win over gate by gate, both in terms of adaptivity and in terms of size. This is the bound that we have, right? So unfortunately, this function, k is the degree, okay? So this function is unfortunately like n to the k. So as a result, we cannot handle, what happens, for example, let me just ask a query, when k is log n? When we're talking about polynomials with degree log n over n variables, we will have a term of roughly n to the k, or n to the log n. That'll be the size of our garbling, and so it'll be super polynomial. So this only handles constant degree garbling, but it basically corresponds to NC0 type of circuits. We can garble them all at once using this particular construction with non-adaptive queries. And so we win on activity. We mostly believe, we don't have lower bounds on circuits, but we mostly win on size as well for this type of thing. And these are just beautiful pictures that Valerio has produced for describing examples of garbling this particular thing and evaluating this particular thing. And what was the point that I wanted to say about this is that reductionism, this is, I think, an example where reductionism fails. So reducing to Boolean gates and just stopping there has failed for 2 reasons. One, because we realized that going below gates gave us an insight into how to garble, and that insight gave us a way to go beyond Boolean gates to polynomials. And so this idea of just reducing to either algebraic gates or this, Boolean gates or ORAM or so forth, is kind of a tricky idea. So as if you're interested in getting the area, maybe try to not have that constraint in your head, because it was certainly in my head for years, and it limited our thing. Okay. One other really cool idea that that unfortunately doesn't win right now, but I think it's a beautiful direction, and this I attribute to Valerio. He has this beautiful construction. So this paper shows a lower bound saying any linear garbling scheme that just does ands is going to require 2k bits, 2 ciphertexts in their model. And so the question is, where should one attack? What word in this sentence, if you're given this sentence as a researcher, what word should one attack? Garbling scheme, yes, you could change the problem. And you could change the problem. But there's one more word. Linear, yes. So one might consider how can we attack the problem of linear garbling by coming up with a nonlinear garbling. And so this is the what we call the circle construction, which for the parameters and for the thing doesn't seem to win in any case, but it happens to be the first example of a nonlinear garbling scheme. So here is the construction. We are going to garble an AND gate by basically giving you a point, gx, gy, some center of some circle, okay? And just like before, what we're going to do is take all the 0 wires and interpolate a circle between those 0 wires. And so the garbling, in order to compute gx, gy, we're going to first compute these 3 points. Those were the 0. Remember, yellows corresponded to the 0 output. So instead of interpolating a polynomial between these 3 points, we're going to 3 points defines a circle. So we'll define a circle, okay? And the distance and the center of that circle will be gx, gy. Okay. So now, when you're given a particular point, like if you're given this particular point, what you do is compute the radius between the distance between this point and that point. And that is the radius of the circle. It'll be the same between this, and this. And so C0 is going to be a function of the radius, and you get those, and you get that. And then for the blue point, for the non one wire, for the other wire, that'll be over here, and that'll define a different distance right here. Okay, and because this radius is kind of a square, it's a nonlinear scheme, and so we thought one could attack this problem of getting beyond this 2 ciphertext bound by using this idea, and unfortunately we can't. We can do it with 2k bits, but for the way that we've approached it, we can't get below that, and we have numerous directions that one might try. But it's food for thought if anybody wants to try to figure that out. And so that's the open question. Can nonlinear garbling schemes beat linear ones? Every assumption or every time I think you can't do something, people show me wrong, so I hope that someone does here. So I guess why study this Yao? I think it's parallelizability is I think where it wins. We'll hear Thursday or tomorrow. We'll hear a different perspective on this with Claudio, I think, and I think there'll also be a talk on speeds. And so we'll hear in this conference several different approaches to this problem. Again, I think that getting malicious security with the parallelizability of Yao is its number one. I had a few slides on why I think those other approaches, these are old though, these are from a few years ago, why I think OT extension and FHE and other techniques weren't going to win. But I won't share them because I think they might be outdated now, and I'll let everybody decide on their own based on Tuesday, Wednesday, and Thursday. And so I guess that's all I have to say for this. Hope you enjoyed.